Good afternoon. My fellow contamination control professionals, my colleagues, people I haven't seen for decades, Tim, others, Tim Russell, it's good to be here. My name's Morgan Polen. As you can tell from my accent, I'm an American. I've been working in cleanrooms for over 40 years. And my subject today is Annex 1 and airflow visualization. My abstract really talking about the difficulties in facility, clean room and barrier system design, or the integration of clean rooms and barrier systems, all can affect our airflow and lead to sometimes intermittent environmental monitoring excursions in critical areas, sometimes intermittent media fill failures, and product contamination. And because the clean rooms and barrier systems are qualified, contamination problems often get blamed on operating personnel as a last resort to get things running when there's no other reasons apparent. I'm going to share some case histories today, talk about airflow visualization, how intermittent problems were related to some facility design issues or operational issues. The video here I have, this is from a facility on the, on the left here. That is a fan-powered HEPA cart, or a cart or trolley used to transfer components, partially stoppered vials, which would be loaded here on the right. And during the smoke studies, we had this issue at the interface. We uncovered this. This facility had been in operation for 6 years. They called us in a panic, had me fly down to Buenos Aires to do a smoke study because the FDA was coming within a month. And they've been operating all this time without any smoke studies. And what we found out is we had this error, and there's actually a HEPA filter above here that their own building automation system had pointed out had been off for over 2 years. People lost jobs, management changed, and the facility had to move on. So a little bit about my experience. I've been in cleanrooms since 1984. And I've done a wide variety of different things in cleanrooms, from semiconductor manufacturing, flat panel display. Spent a tremendous amount of time in Asia with the hard drive industry. And my very first smoke study, I used cigarettes and Polaroid cameras to troubleshoot an airflow problem in a raised floor cleanroom that was making semiconductor devices for the US Department of Defense. And the thing I learned there was really important in contamination control is particle size matters. When it comes to contamination problems, those of you in pharmaceutical manufacturing, anybody ever come across an issue where you pass at 0.5 and fail at 5 micron when you didn't before? Chances are something is broken. And the same is true with smoke studies. When it comes to airflow visualization, particle size matters. And we'll talk a little bit more about that. I have maybe a unique perspective in contamination control because I spent a lot of time flying. I've done projects all over the world. And this picture here is a project I worked on. It's an airborne laser. That's a converted 747 that was converted into a flying death ray. And I had to work on a variety of cleanroom projects for that. I have a lot of experience in cleanrooms, and this kind of matters when we start looking at contamination control. Airflow visualization is an essential tool for contamination control. Can't stress that enough. Clean rooms, clean zones, clean equipment are used to protect products from contamination. Clean environments work by the movement of suitably cleaned and conditioned air, diluting and displacing intrinsic contamination. We use overpressurization to keep extrinsic contamination outside of the clean room. Contamination control depends on clean airflow and clean room, clean air device airflow patterns. Room geometry, equipment, furniture, personnel, and material movements all can impact airflow patterns, and because air is transparent, it's hard to understand. Airflow visualization studies help us understand airflow patterns. This understanding is essential for contamination control and risk management. And the contamination control effect, that's a word I like to use often because it really describes, get some water, apologize. The contamination control effect, when we talk about airflow, is how air moves in a clean room is essential. What's the difference between an ISO Class 1 clean room and an ISO Class 9 clean room? Design considerations, but number one is how air moves. Thank you, Tim. The US FDA requires airflow visualization studies In critical zones, GMP Annex 1 expands upon that for both clean room and clean air equipment qualification, risk assessment, the establishment of environmental monitoring locations, operator training. And for contamination control, as stated in Annex 1, they prefer RABS, or barrier systems. RABS and isolators are preferable to any other approaches. If you use any other approach, something besides a RABS or isolator, you can best be assured you need to have suitable airflow visualization studies. And interesting things to consider when we talk about doing airflow visualization in both RABS and isolators, they have some challenges that we have to overcome. But what is airflow visualization? It's a science of making airflow patterns visible for analysis. It's a science that's actually not unique to clean rooms or to pharmaceutical manufacturing. Airflow direction test and visualization, aka smoke studies, and I paraphrase this from ISO 14644 Part 3, is useful to document, evaluate, and characterize airflow patterns in clean rooms, clean zones, clean air and separated devices, controlled environments, and the interfaces between zones. It's a useful tool for risk assessment, for process simulation. When we do our smoke studies, we do airflow visualization studies, we're meant to do all of our interventions, all of our activities, aseptic activities, and we're intended to do those under smoke. And we do those for a variety of reasons. One is to understand the design, but two is to look at the operator's movements. It's also a record of environmental equipment performance. It's a record of your operations. It's a tool for challenging design and SOPs, and it's a tool for operator training. In this particular video, here's a company that used an outdated design. If you can see this picture up here on the top of the page, this is an outdated contamination control tool. It's a RABS, right? We talked about Annex 1, but the HEPA filters are not coupled to the enclosure. That is a problem. Every single study that we've been involved in where the HEPA filters are not coupled to the RABS has airflow issues that you have to understand. In this particular case, this particular design, they didn't understand it, and where we're looking at is the loading pattern, the loading place for sterilized stoppers. The company got in touch with us because they failed their first media fill. They had a panic. They reached out to the owner of our company, who was a microbiologist, a mycologist. We took a look at it, and we identified they had a serious problem with their airflow, particularly in the loading zone. We came down, evaluated it, and were able to identify they didn't have suitable airflow due to placement of lights and HEPA filters. And again, the filters in the ceiling were not coupled to the enclosure, and that can be problematic, as you can see in the videos. Long story short, 2 years after we did the studies, they had to, well, the company had pulled out the brand new filling machine, redid the clean room and put in an isolator. They never were able to get that line up and running. Why do we do the studies? Well, we do these studies, number one, because we're required to. The US FDA requires us to do airflow visualization. And one of the important concepts to remember is, again, from the US FDA sterile septic guidance, it is crucial that airflow patterns be evaluated for turbulence or eddy currents that can act as a channel or reservoir for contaminants. The video I just played here, play it again. This was a company that made media for bioproducts, and they were failing media fills. Kind of interesting, a media company failing media fills of their own product line, and it was consistent. And they came looking for help with their facility, and they said, look, Morgan, we're only failing media fills by 5 or 7 hits out of 10,000. Just a few help us get past the point. Once we looked at the issue and the layout of the clean room, it was really clear they didn't have a line that was suitable for manufacturing. And after several months, they concurred. Also, we do this because GMP Annex 1, Section 415, says we need to do airflow visualization. And it states specifically, airflow patterns within clean rooms and clean zones should be visualized to demonstrate that there is no ingress from lower grade to higher grade areas, and then air does not travel from less clean areas such as the floor or over operators and equipment may transfer contamination to higher grades. This is an air return. And you can see some of the smoke generated in front of the air return is pulled into the air return. That's why it passes qualification, but a majority of the smoke is pulled upwards into the inlets to the enclosure. Upwards movement of airflow. It was a bad design. The facility was in operation for over 10 years. They had intermittent contamination problems due to the bad design, and it kept qualifying. Again, someone would check the air return with an air velocity probe and then get a reading. But they didn't know how the actual air was moving. The point being, if you take nothing else out of this presentation today, is particle counts, air velocity, air exchange rates, pressure differential, all those things are really important to qualify our clean room, but airflow visualization gives us a visual representation of the contamination control effect. Here's an example. What we're seeing is that is the change room. Now there's a 10 Pascal difference between this area and the area that the door just opened. That's with the doors closed. Once the door is open, several things take effect. One is the airflow inside the smaller room. We have 2 HEPA filters in there. We have 6 in the larger room. The placement of the air returns creates this piston effect. When the door opens, air from the gowning room rushes into the processing room. Right? That wasn't how the room was designed. They didn't understand that. Had the right pressure differentials, didn't have suitable airflow in the implementation. Other reasons why we do the studies, again, Annex 1 tells us we have to do part of qualification. It spells out the tests that we have to do, and the test number here, number 4, airflow direction and test visualization. Can't stress this enough on new facilities. If you're doing a new facility, you're buying a new isolator or filler, make sure airflow visualization is part of your URS. One of the biggest challenges that I face when we do smoke studies for customers is the line won't run with the smoke, right? Because of the optical sensors. And last summer I spent some time in Europe, in a northern country in Europe, and the customer told us, or the end user said, we wrote a risk assessment that states that if the manufacturer says if we run smoke, it could damage the equipment, we're not going to do that. We're going to get around it. Well, I'm not supposed to swear, but that is a BS answer, right? The regulators don't care. You've got to do a study, and you got to do a study simulating your operations, and you got to run smoke or some other way to visually to show that the equipment doesn't affect the operations. And if you can't do it, too bad. I've had this discussion with Scan, Optima, different filling equipment companies, and they get it, but they like to say you don't need to do it, right? Some of them take a very different approach to doing it. Others embrace it. I'm not going to name names, but some companies are a little bit, I'd say, more proactive. I don't want to say better or worse, but a little more proactive at doing it. But my discussions with the US FDA, we don't care. We want to see the study. Prove to me the equipment operates correctly. Work with your suppliers to get around it. We're talking PLCs. There can be a program. It can be done. Every single installation where we put our foot down, they've gotten people in to get around that effect, because it's come back to bite the companies that tried to address the issue with risk assessment. So make sure you plan for it. And this really is an essential part of contamination control. This clean room was qualified. The certifiers were there the week before we came in to do the study, yet one of the filters was off. They leak tested all the HEPA filters. They tested air velocity, supposedly, and they may have. Again, something could have happened between when we came and when they did their testing. Don't know. But the most important point is the end user had no idea they had this problem. So we do this testing, and it tells us in Annex 1, refers us to Section 4.4 and 419. And in 4.4, this is talking about the basics of the clean room, but it does tell us grade A area, the protection of first air. The maintenance of unidirectional airflow should be demonstrated and qualified across the whole of the grade A area. But what is unidirectional airflow? We tend to think we know what it is, but sometimes, is it really unidirectional? Here we have the smoke above the conveyor. This is supposed to be a grade A filling line. This is a grade A area protecting open bottles, and the smoke is moving at about a 45-degree angle. Back when I first started in Cleanrooms, we had this thing, NEBB, we talked about parallelism, and anything greater than 14 degrees we had to make a note of. But is it truly unidirectional flow? Unidirectional meaning moving in one air, but the HEPA filters are here, it should be moving straight down, not at 45 degrees. Earlier we were talking about active air sampling, isokinetic sampling, the probe should be faced into the airflow. Well, if this is really 45 degrees, the probe should be slanted 45 degrees over. And going on 419, Annex 1 talks about 419, and the design technology talking about open isolators and closed isolators. And at least from my experience, most closed isolators that I deal with are typically sterility assurance or hazardous drugs. But we really talk about, again, design of open isolators, grade A conditions with first air protection in the critical zone and unidirectional airflow that sweeps over and away from exposed products during processing. Design of closed isolators should ensure grade A conditions with adequate protection for exposed products during processing. Okay, where processing lines are included in closed isolators, grade A conditions should be ensured with first air protection in their critical zone and unidirectional airflow that sweeps over and away from the exposed products during processing. Is this unidirectional airflow? This is an isolator. It's not perfectly unidirectional airflow. It's actually at a slight angle. This slight angle could have been corrected relatively easy in the design or even in the startup of the isolator. This smoke study led to further investigations from customers, and not inspectors, but the users, was the CMO. Their users called this into question, leading the company with this isolator to make some modifications. Again, talking about open isolators and grade A conditions, we have to go through what is first air. First air, according to Annex 1, refers to filtered air that has not been interrupted prior to contacting exposed product and product contact surfaces with the potential to add contamination. So if you write a specification for unidirectional airflow, that was a problem for these guys. They changed their specification to say first air protection that met the requirements before they put in plastic to make the modifications. And it's important to understand, we have to look at that, what is first air? Now, people will make the argument first air is first air, the air that comes from the HEPA filter. Can we include the diffusers in the first air definition? Right? Can we include a cross piece? Can we include a robot? And the answer to that is it depends. Depends who you're talking to. A couple months ago, while I was in Vienna at an ISPA conference, and a European inspector said, not even the robot should break first air. Well, if that's the case, most modern isolators that are out there today wouldn't meet that requirement. And I challenged him at it, and I asked him about it. I said, look, we understand that we would expect as people move into this that new products coming out, new lines coming out, won't break first air. And you have to address the risk. So it's a changing environment. Talking about RABS, the design of the RABS should ensure grade A conditions with unidirectional airflow and first air protection of the critical zone. A positive airflow from the critical zone to the supporting background environment should be maintained. In this video, we're generating smoke in the grade A air, but there's air returns on the other side. Let me go back here. Maybe I can, hopefully this will start. So there's an air return on the other side of the RABS enclosure. Partially stoppered vials are filing into the lyophilizer via this conveyor, yet it's really clear, and you'll see that air is flowing from the grade B occupied zone through the conveyor, through the grade A zone. And this was a brand new installation. They had no idea what was going on. And with multiple cameras, we make it very clear, generate enough smoke that yes, air from the grade B zone is flowing through the grade A area. And you can see the air return over here. It's one of those things, once you get used to doing, you can tell without running smoke there might be an issue. And what their fix was, they just put up more plastic. They put up more plastic to make the RABS more tight, and then open door interventions resulted in line clears. That was how they addressed it. The point being, this would have been avoided, this problem would have been avoided at the start of the project had they decided to really look at the design, do computational fluid dynamics, model it, and then you can address the issue. And a lot of times, I mean, CFD is a wonderful tool. Can't stress it enough on new projects or even retrofitting projects that have problems, because it allows you to create a model, and with that model, that gives you a tool to make changes before you cut plastic, before you cut metal, before you do these things. And then you can use airflow visualization to help validate it. The background environment for isolator RABS should ensure the risk of transfer contamination minimized. Impact of glove manipulations may potentially compromise first air protection at critical process points. When you do your smoke studies, your RABS or your isolators, operator techniques matter. You want to make sure on your studies that you really pay good attention to the operator techniques and their movements to make sure that they don't break first air. Aseptic technique. And this goes all the way from glove sanitization to when they enter the isolator or the glove ports. Can't stress that enough. And people say all the time, well, Morgan, why are you bothering filming hand sanitization before the operator goes into the isolator? Is it part of your intervention? If the operator is going to remove a jammed vial, it's an intervention you practice. That intervention would include them sanitizing their hands, entering the isolator, inspecting their gloves, picking up the forceps, removing the jam, and then sitting the forceps down or back where they go and exiting the isolator. That would be the full intervention that you would capture, even though smoke is only a smaller portion of that entire test. Right? It doesn't take that long to do, but the whole point is you're simulating that intervention. Understand that. Because multiple times, U.S. inspectors and foreign inspectors have flagged people we've worked with and saying, hey, we don't like your hand sanitizer. It's inconsistent. One facility we did recently, two-operator intervention. They had multiple two-operator interventions. One operator would wear his gloves over the sleeves of his building suit. Another operator wouldn't. The operator didn't bother to do it. It was actually the supervisor. Didn't think he needed to do it. We mentioned to him several times, like, hey man, it's inconsistent. If you're not gonna follow procedures, at least do them the same way. Doesn't matter. Their customer pointed out to them they had the problem. They're being inspected in a couple weeks. We'll see what the U.S. inspectors, the FDA, thinks about those practices. But that stuff matters. It sounds like minutia. It's not necessarily related to smoke studies, but it's part of what you're putting on camera. Background, talking about RABS, the background of the RABS for septic processing should correspond to a minimum of grade B, and this airflow pattern study should be performed to demonstrate the absence of air ingress during interventions, including door openings if applicable. And I'm talking about RABS here, but the same is true with isolators. You should be performing smoke studies with your doors open on your isolators to prove that grade C air doesn't enter the isolator during setup. People argue with me all the time, say you don't need to, it's an isolator, we use VHP, blah, 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 it doesn't matter. The regulators are saying it matters. They just said it in Vienna. It wasn't just the US FDA, it was European inspectors as well. It matters. Why? Because it's important to understand that VHP is not a sterilization agent. It's decontamination only. They know that, they respect that. It's great we do it, and believe me, it's really effective when used properly, but we have examples at Microrite, we have case histories where companies had fungal contamination inside their isolator. And it didn't come from people. It came from the building. Which brings me to another point when we talk about contamination control in general, right? Building leaks. Leaks of water in the interstitial when it rains is more common in pharmaceutical manufacturing than most people are aware of. It happens. It happens a lot. And one of the things I try to tell people when I teach a general course on contamination control is if you're making medical products and you have a building leak, a water leak in the building that you make medical products, you need to treat that as serious as a fire. Because it doesn't necessarily mean people are going to die, but you should shut down production. You should find out where the leak comes from. You should remediate it, fix the leak, and remediate the water damage. Because multiple times, just from experience, we get called into companies having contamination problems, and as we start finding, oh, we got fungal contamination, what's the source of the fungal, what's the species? Oh, that's probably from building, from water damage. And it's important to understand. So this is why we have to do this testing, and it's important to take it seriously. Addition Annex 1 talks about the speed of the air supply in the unidirectional airflow systems. Also, where do you place the probe? Airspeed should be designed, measured, and maintained to ensure that appropriate unidirectional air movement provides protection of the product and open components at the working position. For example, where high-risk operations occur and where product or components are exposed. Unidirectional airflow should provide a homogeneous airspeed of 0.36 to 0.54 meters per second. That's at 90 feet per minute. Gordon talked about that. That's an archaic term we keep around. 90 feet per minute, we like that. The US FDA likes that. You can certainly have lower airspeeds, but it's important to understand airflow visualization studies should correlate with that speed measurement. This is an example, if you can see here, this is our tracer particle, our smoke manifold, if you will. It's 6 inches below the HEPA filter. This overhang design provide unidirectional airflow when the operator opens the enclosure opens the door to the enclosure. It's 90 feet per minute, yet this is our work surface. This is where they set up and they prepare components to go into the RABS. From the smoke, what's happening, it comes down 90 feet per minute and it makes a U-turn. It short circuits to the inlet of the enclosure, which is directly above where the operator is standing. You're not getting clean air to the work surface. We are opening up clean systems. It was validated. They were making product. Everything was good until they did the smoke study. And the first smoke study they did, it showed it was wonderful because they used a heavier than air water fogger, and it showed they had perfectly fine airflow. We'll talk a little bit more, but you can see the real issue, right? We weren't getting first air to where the products were being handled. In addition to that, we should use airflow visualization for environmental monitoring. This is a funny video. Watch the cable. The cable gets wrapped up in the SAS sampler. But again, our number of sample locations and where they're based should be based upon our smoke studies. Where we place the probes should be based upon to get us the most amount of signal to indicate what's going on. In addition to that, operators, right? Movement of personnel should be slowed, controlled, and methodical to avoid excessive shedding of particles. One of the biggest things we see when we do smoke studies are operators moving too quick. Particularly when you're doing studies and you're there for weeks on end or a month on end, the operators tend to get a little bit more relaxed. They forget they're doing smoke studies. And then they start acting like they normally do in production. You know, and we typically ask them, how fast do you move during media fills? Well, this is how fast I move during media fills. Well, that's pretty fast. Now, in other parts of the world, like you go to the Far East, the operators are moved ridiculously slow because they know the cameras are on them. So when it comes to hand sanitization, they literally move this fast. And you're there, and you're waiting on them, and you know they don't move that slow in production. You know they don't move that slow in media fills. But they do it because suddenly they know there's a camera in front of them. So again, this is a picture, this is from a smoke study. You can see the operator's head is over the bowl, right? And smoke is obviously flowing over his head directly into where sterile components are. So this is why you want to review smoke studies and make them part of the operator training program. Can't stress that enough. Now watch this video here, see if you can see what's wrong. Anybody see any problem with the video? That's an active air impactor, right? That's an active air sampler. The operator is using the sampler as a shelf for the tri-clamp for making the aseptic connection. Would that be a problem? I think it's a problem, right? The aseptic experts I work with think it's a problem. The customer didn't think it was a problem. They thought, well, what's the matter? Right? There's no plate there yet. Well, the plate should be there if you're doing an aseptic connection, shouldn't it? Of course it should be. You should be monitoring it. And these type of things, and it's one of the best things about doing studies, if you're doing them, is to watch it in real time. Here you can see an example from a study where QA, validation, and manufacturing were behind the isolator. We're feeding 4 cameras into the screen, and they could see things in real time. They didn't like something, they could stop and say, we're going to redo that. And that's one of the most important benefits, I think, of doing smoke studies in general, is that real-time feedback. You have the opportunity to coach your operators, right? We have SOPs. SOPs are great, and people should read them, but the problem is the implementation. And by having a team of people watch the operators perform it, you can tweak, you can modify, you can figure out issues like ergonomics. One facility we did, they had an operator that came up to be about this tall. And the partner that she worked with was about this tall. And they had to change positions because of the ergonomics, being able to reach through the glove ports into the enclosure. And smoke studies help put that on camera, help you film it, help you get an understanding of what's going on. Watch this video, this training video. It's loaded with sterilized caps. It's an eye drop facility. You see that? We call that spray and pray. He sprays before he goes in, and then he doesn't sanitize his hands at all. He's handling the step ladder, he's handling the bag, he's handling the curtains. One of the problems with cleanroom curtains is they're not treated like doors or walls. In aseptic operations, you're not supposed to touch the walls, right? You're not supposed to touch a door. If you touch a door, you sanitize your hands. The problem with curtains, people handle them all the time. You can't clean them very well. You can't sanitize them very well, and you need to understand it. His hand is dirty now, and so is his suit. All these things come in contact with the curtains, and this is one of the things that smoke studies help you understand what's actually going on, because you're looking at it. Airflow visualization is also a really good tool to help optimize airflow patterns, supply and return air placement, balance the clean room, placement of equipment, and it's a tool to optimize operator positions. This is an example of a smoke study. We're generating smoke. You see the manifold on the outside of the isolator. Customer didn't want to do this, but it was a CMO. Their customers made them do smoke studies, smoking the outside of the enclosure, outside of the isolator, to prove that smoke didn't go inside the isolator when they did set up. In this case, I think they're setting up the stopper bowl. One of the things that came out of it is the customer discovered they couldn't have more than 2 doors open. Otherwise, they had cross flow through the isolator. They couldn't have opposite doors open. The doors had to be open on one side, otherwise they had cross flow through the isolator. In addition to that, they discovered this really important thing. which I've been talking about years, is the operator, how the operator gowns when they're working in the open isolator. A hairnet and a beard cover. Just a thing from contamination in general. A hairnet is not a contamination control garment. It's a hairnet. Someone has their entire torso inside your sterile or inside your isolator. Yeah, you're going to use VHP, but what are they leaving behind? So the results of it, the company said, hey, we're going to change. We're going to gown sterile. Isolator doors open. We're going to gown in grade B. We're going to have an extra extra person to help keep the gloves sanitized during these operations, and we're going to do a better job. But again, the contamination control effect, entire grade A zone associated environment should be evaluated. The isolator, the RABS, the BSC, the HEPA cart, the ALUS, the automatic loading unloading system for lyophilization, the background room, in-feed and out-feed, mouse holes, pass-throughs, airlocks and doors, particularly material airlocks and personal airlocks, air returns, and also don't forget trash chutes. Should be evaluated. And again, special emphasis should be when doors are open for equipment setup. Last points I have, I don't know how I'm doing on time, but common mistakes in airflow visualization is a jetting effect. Most companies, when they do airflow visualization, will have a manifold configuration to cover a larger area, but only have orifices or holes on one side. What this does is this jets or ejects the tracer particles or the smoke or fog in a single direction. The FDA is aware of that and challenging that. You cannot do that. Because what happens is, whether this is a water fog, this is a glycol fog, regardless of what you're doing, that jetting effect overcomes the local airflow. And that can influence your results. It can influence the conclusions you have. It can make it look like this is a unidirectional flow clean room. It's not. This is just a photo setup. It's not a clean room at all. Yet the smoke is being injected downward. Same over here. It's downward, and you can see it loses its energy and it starts to spread out in the room. And here's a video sent to me by a good friend of mine, the smoke studies, and here he's ejecting the smoke directly over the operator, and it's going in a downwards motion. It's one common mistake. Another common mistake is using heavier than air than cleanroom foggers. The photo on the left, the video on the left is from a friend of mine from Cuba. He called me up and he's all excited. He got a 8,000 euro fogging system for his clean room. I said, hey, take it to your conference room. This is a conference room. It's no clean air. He's shooting the fog directly up, and once it overcomes the jetting effect, it settles because it's heavier than air. How can you possibly test a clean room with a fog that's going to sink on its own? You can't identify dead spaces. Very difficult to identify upwards movement of air, and very difficult to identify turbulence. On the right, this is it's a glycol fogger. Now here, switch to the nitrogen fogger. No HEPA filter action. HEPA filters are off. This is the nitrogen fogger, and what's happening? The fog sinks on its own. There is no airflow underneath those HEPA filters. And now we move it underneath the fluorescent light, and it still looks like it's got unidirectional airflow. And this is problematic. Now we're going to see it's going to cut over here to glycol under the same HEPA filters in a second. Here we go. And you can see it's obviously clear this fog is, the smoke, the tracer particles are spreading. Not going downwards, moving because there is some airflow in the room, but it's clear that the HEPA filters are not on. The problem with heavier than air clean room foggers is they're clean. Right? People like to talk about cleanliness when it comes to smoke studies. It's clean. I want to be clear to everybody. There's nothing clean about doing a smoke study. And why is that? Forget if we're using water, nitrogen, or we're using a smokeless system. What are we doing when we're doing a smoke study? We're simulating our operations. If you have a filling line, you're going to simulate all your interventions, corrective interventions, spills, broken glass, setup and assembly. You're not going to assemble your filler, do a smoke study, and start production. You're going to assemble your filler, you're going to do a smoke study, you're going to simulate filling and closing operations, you're going to be running water into vials, putting stoppers in, right? Simulating broken glass, simulating jams, simulating cleanup, and then you're going to break the machine down and sanitize and sterilize all the components. It's not a quick test. If you're going to do a comprehensive smoke study, it's not a simple test. You go in. You have to plan on it. You have to plan if you're going to do a comprehensive study. And it's not going to be clean. You have to disassemble the equipment anyhow. And with that, I conclude. Any questions?
Morgan, thank you again. Well done. You know, everybody's got a passion, right? And Morgan's is airflow visualization studies. Yeah, so a lot of good examples there. Okay.
Again, sorry. Morgan, how often is it expected to conduct a smoke visualization airflow, besides from new facilities, reclassification of a clean room, and retrofitting?
Thank you for asking the question. Did everybody hear the question? How frequent we should do the study? So, the answer to that, like most of my answers, it depends. But let's be clear. I'll give you my educated answer, if you will, or my uneducated answer. So if you're a compounding pharmacy in the U.S., USP 797 for compounding pharmacies requires airflow visualization with qualification of the room and to be repeated every 6 months. Okay, and why every 6 months? Because in U.S., compounding pharmacies are typically a horizontal flow bench. Maybe we're lucky, a biological safety cabinet, at least it's better because you got a sneeze guard. I think it's really important to have a sneeze guard, right? Because masks don't stop sneezes. But every 6 months, because we're typically starting with an empty bench, and the configuration of the components matter, right? Typically, the operator's going to start his day setting up his compounding center. You know, his pump, his syringes, his wipers, whatever he has, he's going to do it a certain way. And he's going to compound. And we do it every 6 months because we want to make sure it stays the same, that operators don't get lazy. And they do. I have a good friend of mine at the FDA said they reviewed some smoke study videos of a compounding pharmacy, and the technician was wearing shorts. Can you imagine wearing shorts? What's the matter? It's horizontal flow bench, right? But honest to God, that's how they operate. So compounding pharmacies make sense every 6 months because the variables are people. People change jobs, people get lazy, it's very manual, the layout. You get a person who's left arm or right-handed, person who's left-handed, that can change. Now let's talk about pharmaceutical manufacturing. Yeah, I think it's the BSI's version of ISO 14644-2 as a table where they claim every 4 years. I think that's irresponsible. Pharmaceutical manufacturing. Why I say that? Because I spent a lot of time in pharmaceutical facilities, and I see facilities go to shit, pardon my American there, quickly. Some are not well maintained. I've seen sections of the clean rooms that the floor's not clean. I see holes in walls, I see rust, all these things. So I'm preference that I would say every 2 years. But again, if you have a well-defined program, I mean, your CCS is supposed to take care of that. I personally think 4 years is far too long. I think 6 months is just, for USP 797, I think it's fine. Because I have a love-hate relationship with compounding pharmacies. But I think 6 months is good for that. So I would say balance 2 years. Any other questions?
You take a break while I run over there with a microphone.
Well, I can't hear so well, so it might be better if I...
My name's Darren Young, I'm from Meisner. Do you have any experience with doing your airflow studies and statically charged surfaces?
Yes. So static charge. So static charge affects particles. We call it electrostatic attraction. So I haven't seen an issue with the smoke I'm using sticking to surfaces, but I had seen water droplets. So Yes, I mean, static charge is something that the life science industry is woefully negligent in understanding. You see that in medical device facilities where you have entire gown rooms with ionizers, right? What is that going to do?
Okay.
Right? But not specifically affecting the flow of the air.
No, because I read a study from Microrite in terms of basically statically charged surfaces actually attracting particles.
It does,
Yeah,
absolutely.
So I work in single-use technology, so plastics are statically charged. So we're starting to see things like this, and it's interesting.
Yeah, well, we see it. Well, I think we definitely see static charge effect on particles, particularly in particle transport. You know, and Hazim's going to talk about that tomorrow. But yeah, static charge will attract particles, retain particles.
Okay.
And everyone has an old TV, an old CRT TV. You notice how dusty it is?
Yeah.
That's
All right, thank you.
static
Yeah.
charge.
Thank you. Anybody else would like to put a question to Morgan?
Am I done?
Okay, I think so. Morgan, thank you again. Really appreciate that. We've earned ourselves a little bit of extra time.